Okay, so we were talking about this time based DC-DC converter, how you build the control loop in time domain using VCOs and VCDLs. So we can build all the integral, proportional and derivative and cascade them, and we know delays are added or phase are added by cascading. So simply we will get the output voltage which will have all the three components, your proportional, integral and derivative. And we know what are the proportional, integral and derivative in voltage domain. We can simply map them and find KVCDL, KVCO and KVCDL1, KVCDL2 and RDCD basically. So if you want to model, we can model like KVCDL is your proportional gain, and then KVCO by S will give you integral component, and this is your derivative component which have one pole. We have to make sure this pole should be outside your UGB so that it will behave like a differentiator. So 1 over 2 pi is the gain of your PM, basically the modulator phase detector. Here it's a modulator is nothing but phase detector. So just like in the voltage domain we had a 1 over Vm, here your total phase is because 0 phase difference correspond to 0% duty cycle, 2 pi phase difference corresponds to 100% duty cycle. So and so that's why we have a gain of 1 over 2 pi. Then Vin is your power stage and then HLC. So your if you do the loop gain analysis, you will see a similar behavior here. You will have two zeros and how many poles? In this case, how many poles? Yeah, one outside UGB and one at origin which is integrator, and two poles from complex poles from HLC. 0 to pi. No, not 0 to pi, it is 0 to 2 pi here. There are two phase detectors. You can build if a simple, let us say XOR gate. So in that case it will be pi, the range is only pi, it will saturate at pi. But if you are doing using flip flop PFD, that will give you 2 pi phase difference. So it depends how you implement it actually. So in this case we have implemented simply using SR flip flop. So you have a two clocks with a phase difference. So if I set at one edge of the clock and reset at the other edge of the clock, so your total range you will get 2 pi there in that case. So the way we implemented it, instead of using a VCO which we call voltage control, we are using current control. So we are controlling the delays with the current, which means and my feedback voltage and reference R voltage. So I need to convert that into current, and we can simply use transconductors. So what we are using here at the input, you can see this is actually your derivative component because it is having a high pass filter first order compared with Vref. So this will be biased at Vref, so that we get only high pass component here, it will not pass any DC component. This is the proportional, so we simply compare Vref with feedback voltage, and then this is your integrator which is VCO. So you can imagine this is your VCO and this is your VCDL. So what we have done actually, instead of using two separate VCDLs, we know, I mean we are converting voltage to current, and we have a separate voltage to current converter for the two. So we can sum up and use only one VCDL. So one VCO for integrator, one VCDL for proportional and derivative, and P and D are already added in the current. So we don't need another VCDL here. You could have done, I mean you could have separated it out and put it, this output should have gone to a different VCDL, but unnecessary we don't, I mean usually we don't need actually. I mean you are already getting a P plus D component, so why do we need add one more this VCDL. So another advantage is like it's you can see it's a fully differential, okay, and the advantage of fully differential is that relative loop delay is almost 0 here. Let us say instead of using this, I could have used only VCO output here directly, not the VCDL, correct. Now what would happen if this VCDL delay changes, this VCO delay will not change. So across PBT, look at a free running delay at a free running frequency, they may have some delay, okay. So and if those delays are matched, then relative delay is 0. But if they are not matched, then let us say with the temperature or process this delay is changing and this remains fixed this edge, then this will add to a loop delay and it may hamper your transient response. But in this case, let us say with the PVT, this delay is changing, this is also changing. So, both are changing in the same direction. So, relative delay is as such 0. So, there is no loop delay as such here. The only delay you will get in the power stage due to finite on and off time, rise and fall times actually. So, the controller has no delay, just like in the voltage mode we have a reset time delay, your comparator had delay, all those delays are 0 here actually. And that was the main reason we can push it at much higher frequency. So, at one edge we set, at other edge we reset, that is it. So, this SR flip flop will simply behave like a phase detector. So, this was the chip we implemented. So, this is your power FET, obviously power FET usually are bigger, and this is the controller. The advantage is the controller is very small here because it is hardly using any large passive components. We have some capacitors here. One was required for your derivative component, the first order high pass filter, and then we have some decoupling capacitors actually, but they are very small, like order of few picofarads, like less than 10 picofarad you can say, compared to what you would have required, let us say 50 to 60 picofarad capacitors in the other case voltage mode. So, and most of the time if you compare the controller size with the power FET, usually you may see 50-50 or 40-60 ratio. Here it is much smaller actually, maybe 25% area is taken by controller and 75 is taken by power FET. So, if you are limited in area and you can reduce the size of your controller, it will give you more room to have a bigger power FETs and you can have a smaller RDS on actually. So, we implemented for 10 to 25 megahertz and maximum current was 600 milliamp. And this was consuming 2 microamp per megahertz. So, another is a Q current is very low here actually, quiescent current. So, at 11 megahertz it was consuming 22 microamps, that is why we are quoting is 2 microamp per megahertz. So, this was published in both VLSI conference, and VLSI conference is a symposium actually, not the one which happens in India. This is a separate symposium on VLSI circuits. And then JSCC also general paper we published later. So, these are the outputs of like two phases, VCO plus and VCO minus, and this is your final PWM which gives you the phase difference between the. So, duty cycle will be nothing but the phase difference between the two. I mean you can say that okay, this edge is not synchronized with this because we are taking VCO output, not from the VCDL. VCDL will also have some delay. So, we took the VCO output, that is why you are seeing that difference. But ultimately the difference between this edge and this edge is nothing but the duty cycle, that is it. This was the transient response. So, 100 milliamp to 600, which is 500 milliamp load step, and undershoot overshoot is roughly 660 millivolt here. This is under the lock condition. So, if in the open loop you operate, so the loop will never force to lock the two VCOs. So, both VCOs are like on its own and they can go anywhere actually. So, that is why you can see frequency is moving all over the places, but the moment we close the loop, both are locked at 11 megahertz here. This is the frequency at different efficiency at different frequency and output voltages. So, the maximum we achieve at this one 11 megahertz and 1.4 volt, and obviously the switching losses are higher at higher frequency. So, 25 megahertz will give you lesser frequency because CV square F losses are higher. So, yeah, so this we implemented in 0.18 and 220 nanohenry inductor and 4.7 microfarad because we are running at beyond 10 megahertz. So, we do not need microhenry inductors here. So, then another advantage is we can go for a multi-phase. I will talk about multi-phase, the basic concept of multi-phase later, but just to give you an idea actually, the benefit in using multi-phase here, because VCOs are ring oscillators and inherently we have multiple phases here. So, all you need to do just tap all the phases and pass to different power stages which will have its own inductor. The capacitor will be common. So that's how the multi-phase is implemented. It's like a parallel converters, you can say, and the load current will be shared among all. So let's say if I have a 1 amp current and there are 5 phases here, so 200 milliamp will flow in each phase. So that's how you reduce the power stage current. Your I square R losses will be less compared to the single phase. So when we implement very high current, let's say 10 amp or so, the only way we can go is multi-phase. Single phase, it's we cannot handle, it's very difficult. So that's the advantage. But if let's say you have to implement the multi-phase in standard voltage domain, so you need, and these phases are equally spaced, so we need multiple ramps generated at different phases. Here we don't require, I mean we are getting all the phases for free actually. All you need, just put the same copy of the same VCO, sorry not VCO, the VCDL1, VCDL2, and replicate them and just feed them different PFDs, and that will drive your power stage. That's it. So this also, this one we went up to 70 megahertz, 4 phase time based buck, and peak efficiency 87%. So, and since we are using more phases, so the power consumption at 30 megahertz is 90 microamp. So per phase here it's roughly 3 microamp, which is almost similar to what we have in the previous. We had a 2 microamp, it's 3 microamp. So again you can see the, I mean this is your power stage, and look at the controller size, it's pretty small. Okay, then recently we started doing LDOs using time based. So and we already talked about what are the issues with the LDOs, how you compensate it, and why it require compensation basically. So we know there are 3 poles in the whole system. One is with your error amplifier, and most of the time we make sure that the error amplifier pole is pushed outside your UGB. Then we are left with 2 poles. One is your gate of your power pass FET or power FET, and then output pole. So usually we use a dominant pole compensation or Miller compensation and make sure that the pole at V gate is inside your UGB and this output pole is outside your UGB. So which means we are limited in bandwidth, and PSRR will also degrade. And if I want to increase the bandwidth, then what I need to do? I mean the only way to increase the bandwidth, I have to make sure that, so increasing the bandwidth along making, and so basically we have to move both the poles at higher frequency. So let's say I have designed something for this LDO for 60 degrees phase margin, and I want to increase the bandwidth. I have to make sure both pole moves proportionally so that your phase margin is maintained. So which means I cannot put a large cap here, very large cap at the output. If I put a large cap here, then even usually the problem happens at light load. At light load it will start moving inside, and so then again you have to limit the bandwidth or make the output pole dominant. Output pole dominant means you have to make sure the impedance at this node is very small. So you may require to add some source follower or some buffer, so that basically the R out at this is much smaller, so that this is pushed outside and this will start dominating in that case. And we know at higher load this impedance will go low, then again it will start moving outside. So we have to make sure the separation is again maintained. So the GM requirement will be much, I mean not the capacitor requirement will be much higher at maximum load. Okay. So these are the issues, like there are the trade-off between bandwidth and your PSRR and your transient response, and obviously the everything cost. If I want to improve the PSRR, I have to increase the bandwidth, and increase the bandwidth means higher power consumption. So what we did actually, again the same concept, use 2 VCOs which will act as a reference and feedback, and now I am using PFD. In the previous case I was using locking only frequency, now I am locking phase also, so I need a charge pump. So these pulses, because you need to remember here in the previous case I needed an output as a PWM, but in a linear regulator there is no PWM. So I need to convert that time into voltage back, and that's what happening in this charge pump. So phase detector will give you the signal more looking like a PWM, and this will be converted back into a voltage by modulating this current. And then you have a low filter, basically that will filter out all the high frequency signals and give you the DC. So this loop filter is basically, so now we have two integrators here, one is VCO, another integrator is in the charge pump, because current is dumped into a capacitor. So I need 1 0 here, so two poles are there, I need to cancel one. So this series R will add a 0 and it will cancel, and this capacitor will cause another pole which will be at RLF and multiplied by CRF. So 1 over RLF CRF. So this parallel combination of these two, we have to make sure that is pushed outside your UGB, otherwise it will become unstable. So now this is behaving like a unity gain feedback amplifier. Okay, and if you look at a LDO, LDO is nothing but, I mean, it's a non-inverting amplifier, but with a high current drive. That's the only difference. So this cannot drive high current, so we need to add power fed. So this is behaving like a, we can use it as an error amplifier and connect the PMOS at the output, this, and it will now start behaving like an LDO. Now we have two poles here, I mean two additional poles. So we have two integrators, and then one pole is at the gate, just like a traditional voltage based LDO, and another is at the output. So we have to make sure that one of them is cancelled out. So we have added only 1 0. Now we need to cancel one more pole here. So I need one more 0. So what we did actually, we added a feed forward 0 here, but through this GM. So now you have two zeros. The 0 due to this GM will be beta KVCO into ICP over 2 pi GMZ. And if you do a derivation, you will find that actually for that, or you can refer to the paper. We have given the details about how this 0 comes. All you need to just apply KCL here, you will get. Yeah, one is outside your, so in this case you require 3 zeros, So we have to make sure one of these poles outside your EGB, just like a traditional voltage mode LDO. We cannot have both output and gate, this pole at gate inside UGB. So that requirement remains there. You have to make sure that one of these are outside UGB. So only one pole is left, so we need to cancel only one, whether it could be output pole or pole at gate. Okay. So the advantage here is this error amplifier is behaving like an ideal error amplifier. I mean, your gain in the standard voltage mode, gain is limited by GMR out. Okay. Here there is no GMR out as such, gain is not limited by that. I mean, you can say that okay, your impedance is limited by this node, okay, but it does not matter that impedance, your gain is, so even no matter what you have, if there is any error, that will be integrated into this VCO and it will correct. So ideally it has infinite gain actually. So you can build a like 200, 300 dB kind of a gain, which is not possible with the voltage mode. So your accuracy will be only limited by the offset, not by the gain here. And second advantage is, now I can build a very high bandwidth amplifier without burning too much current here. And you can operate at lower voltage also, because I mean, if you want to build a very high gain error amplifier, then you need to cascode obviously, or gain boosting, and you cannot operate at very high voltage. Here all those requirements go away actually. So the same concept which we use like multi-phase in switching DC-DC converter, you can use a multi-phase in LDO also. So the advantage here is, I have all the power feds parallel, connected in parallel. You can think about there are multiple power feds, each one has its own this PFD and charge pump, but we are using common VCO, because we cannot have multiple integrator in one loop and they will start fighting with each other. So we can have only one integrator, but we can have multiple PFDs and charge pump. So each will have its own control, and so now the advantage here is, depending upon the load current, you can decide how many phases needs to be turned on. So let us say I want to cater 10 milliamp. 10 milliamp is, so you will size your power FET according to 10 milliamp. Now let us say I have 10 phases, so I will size, so each phase is carrying 1 milliamp, so I have to size one power FET for 1 milliamp only, and now they are connected in parallel. So whenever my current requirement goes above 1 milliamp, only then I will turn on second phase. When it goes more than 2 milliamp, I will turn on third phase. So that's how I will keep on turning on and off depending upon the load varies. So the advantage here is, now the capacitor seen at the gate in light by each phase is very small. So you can increase the bandwidth without increasing too much current. And another advantage is, look at the light load. So if you oversize your power FET, then you go very low current, that will saturate, that will go in sub threshold and saturate. It may saturate also, but in this case your power FET is very small, so at very light load only smaller component is on, and even you can make it even smaller whatever you want to. You can keep one phase, let us say, to handle only 100 microamp, so that, and that will be only that port will be on, and the gate cap will be very low. You can still have a very high bandwidth without needing very high current basically. So that's the advantage here, if you scale number of phases or power FET sizes with the load current. It's a similar concept what we used in DC-DC converters to reduce CV square F losses, if you remember, segmented FET. So the same concept is applied here actually. So it will give you very low IQ with high bandwidth. So this multi-phase also we published last year. This was 2018, that was 2019, the multi-phase one. So I mean everything looks good, but there are obviously, since it's a new technique, so it will come with some issues and we need to find a solution for that. So one, we talked about your cycle slip. So the moment your phase crosses, because phase will always fold back to 2 pi. So from 2 pi to again 4 pi. So it will behave like the range is only 0 to 2 pi. So the 2 pi will become 0. So duty cycle will reset to 0. So let's say you are operating at a very high duty cycle, which is shown here, let's say 90% or so. Transient comes, and so your phase will change and it will accumulate and it will try to go to 100%, which is 2 pi. The moment it crosses 100%, it will cross and make it 0, and you will see output will dip. So which means, I mean, this is more like a failure actually, system failure, because it may go out of regulation and reset your whole system, which is unacceptable. So we have to prevent this. So how we prevent it? So what we have actually, I mean, we know the phase will only accumulate when there is error, and if I know how I can define a maximum and minimum duty cycle, and whenever I detect the maximum or minimum duty cycle, I make the error voltage 0. So that's what I am doing here. So duty cycle limit or cycle slip detector. Cycle slip detector is more like a you can say, which detects 2 pi phase. So either you can look at the duty cycle or look at the phase difference. In both the cases you can take the decision. So whenever it goes 2 pi, you make the error voltage 0. So what we are doing here, whenever this duty cycle limit or cycle slip is detected, so we know one end is connected to Vref, other is connected to VFB. So we remove the VFB and connect Vref through this FET and make the error voltage 0. So when the error voltage is 0, the phase will not accumulate and it will not try to go towards 2 pi. Okay. And when it comes back to your steady state, then you again, it will automatically, basically your D lim will go 0 in that case. It will only reach when it tries to cross the maximum duty cycle. So it will come back and then output will get settled. So you will not see this kind of behavior. You can see this. This is with cycle slip detector. When we apply the load current, the duty cycle is changing and going to 2 pi, and my voltage dips like this. Undershoot, you can see it's more than 1 volt actually. So if you are operating at 1.2 volt, it will go to like 200 millivolt or so. And the moment I have a cycle slip detector, then it remains constant. Another problem is offset due to VCO mismatch. I mean, so far we are considering that these VCOs are matched. So if they are matched, then when VFB equal to Vref, then the frequency will also be same. But if they are, let's say there is a mismatch, then what would happen? Even if the VFB is same as Vref, the frequency will be different, and when the frequency is different, the phase will get accumulated. So what will happen? Ultimately the loop is trying to lock the frequency. It does not care about what the input voltage is. If they are not matched, then what will happen? The frequency will match at a different feedback voltage than Vref, and that is what will cause the input referred offset. So if we want to calculate, we know the KVCO. KVCO means how much delta frequency per volt. So let us say this is 1 megahertz per volt, and the free running frequency is 10 megahertz. Means when in the steady state, when VFB equal to Vref, then both the VCOs will have the same current, and depending upon at what frequency, at what bias current you have in that GM, which we have a like V to I converter. So half of the current will flow in both. So that will define your free running frequency. So let us say 10 megahertz free running frequency. I am taking the same case what we had in the 10 to 25 megahertz buck, the first buck which we had. So, and the requirement for there was 10 megahertz free running, and the KVCO we required was 1 megahertz per volt. Now let us say 1% mismatch in the VCO. So 100 kilohertz offset in the frequency, correct. So 1% mismatch means 1% of 10 megahertz is how much? 1 megahertz?
0.21 megahertz.
Yes, so 100 kilohertz, huh? And in terms of KVCO, how much is this? 100 kilohertz with respect to 1 megahertz per volt, how much is this? 10%, huh? So 10% means, and if you translate back into the voltage, it will looking like a 10% offset. So the 1% mismatch will be a 10% offset, but now my Vref is 0.6 volt, not 1 volt. So the 0.6 volt again will scale, 1% will scale to 16.67%. So the 100 millivolt, I mean, so 1 megahertz per volt means 100 kilohertz per 100 millivolt, correct. So 100 kilohertz mismatch will cause 100 millivolt offset in the voltage, input voltage, and my Vref is 0.6 volt. So 100 millivolt of 0.6 volt is how much? 16.67%. So this is the offset you will get actually, and if you have a Vref 1.2 volt, then it will go half. Okay, it will become roughly 8.4% or so. So it's still very large actually. I mean, we know band gap can give a maximum 1.2 volt, and if I am operating at 1 volt or 1.2 volt, I am forced to use a lower Vref. I cannot use 1.2 volt and get a 1 volt output in the regulator, that is impossible. So that is why we most of the time we use lower Vref, and lower Vref basically will translate into more offset, because we have a gain here, beta factor. So how do we fix this? Which means we need to cancel this offset just like we do in the standard voltage mode. So what we do actually during startup, again if I connect both the VCOs input to Vref and see if there is any frequency difference in the output or not. If there is a frequency difference, that means there is a mismatch, because both voltages are connected to Vref. So if they are matched, both should operate at same frequency, but if there is a frequency mismatch, they will not operate at the same frequency. So this PFD will detect the frequency, and I have an accumulator that will accumulate the frequency error and control one of the VCOs. So if let's say this guy is higher, you can reduce this frequency or increase the other frequency, whatever you want to do. So that's how you correct the offset. So the another advantage is, I am only showing the VCO here, but if you let's say you have this kind of implementation, this guy, so everything will be in the loop. So any offset due to this diff pair will also get cancelled out. So the offset due to mismatch in VCOs, offset due to mismatch between these diff pairs, everything will be taken care in that one single FLL. And after that, you connect your feedback voltage back and close the loop, and it will run in the normal operation. It's like a static offset cancellation which we were doing in the error amplifier. You remember, we were introducing the offset in one direction by cancelling the offset. So if a positive offset, we were introducing negative offset, and what we were doing, we were tying the input. We were making the error 0 and monitoring the output whether it's a 1 or 0, and then keep applying when transition happens. The same thing is here, but everything is in the time domain. That's it. So this is with offset, and we have seen like 0.17 volt offset at 30 megahertz. Due to mismatch, we were seeing 5 point, which is like much higher than 1%. 5 megahertz out of 30. So it's a huge offset. Huge mismatch you are seeing. Now we turn on the FLL and correct the offset, and so 170 millivolt now reduced to 5 millivolt. So, and how much offset maximum accuracy you can achieve, it will depend the resolution of your FLL. So more number of bits I have in this accumulator, I can tune with a finer resolution, and I can reduce this further. If let's say my requirement is less than 1 millivolt, then you simply increase the number of bits here in the accumulator, and you can get